Okay, so welcome back if you've been here before. Welcome if it's the first time. Today I want to talk about things that rotate, things that spin. So here's kind of the idea of what I want to talk about. The first thing that we're going to do is we're going to kind of call back to previous problem that we talked about in an older stream. I'm going to kind of recap it, go over what we found on it. And from that example, I'm going to introduce the ideas of angular momentum and torque. And once we have those, we find a very important thing. If you've seen this before, or these streams before, you know that we like to find conservation laws. Conservation laws are very important for solving problems because they can really simplify things that we care about. So angular momentum, it turns out there are certain cases where it is also conserved, so we are going to write down a new conservation law. And then we're going to use that conservation law both to write down centripetal forces, which we'll talk about later, but essentially they are forces that keep things traveling in circles. And then we're going to apply this stuff to several cases. So 3 and 4 are going to kind of be mixed around. I'll probably talk about certain things, or I'll definitely talk about certain things before talking about centripetal forces, and then go from there. And so, of course, as always, if you have any questions, feel free to leave them in the chat. I have it open, so yeah. Okay, well, let's go ahead and get started. So, a few streams ago, we talked about this example where I have a ball or some mass and it's sitting on a table, my crudely drawn table. And so we have some ball here and it's attached to a string. This string goes to the center of the table. And if I have some side-on view, the situation, the situation's gonna look like this. I have my table like this. I have my mass or my ball, whatever it is. I'll just draw it as a red mass here. And it's connected to a string. And this string goes through the table, and we'll say it's connected to the ground through some eye hook. So what we said is, okay, what happens if this string can stretch, and more importantly, the string stretches and is completely relaxed when the mass sits right at the center of the table. Okay, so what we found when we did this was that we could describe the motion of this mass in a fairly general way. So I can write down the position of this guy as a vector. So we'll just come up here, and I'm going to write down my coordinate axes. I'll call the horizontal E1 hat, the vertical E2 hat, where these are just my unit vectors that I use to define my coordinates. So I can write my position vector for this guy as x1 of t, so the piece of the vector which lays in the E1 direction, plus the piece which lays in the E2 direction, E2 hat. Where of course our position vector is going to be this vector. I'll use a different color, use blue here. this is x. It's my position vector. Okay, and what we found is that both of these components of this vector I could write as ai cosine omega t plus bi sine omega t, where here I is equal to 1 or 2. I have a1, a2, b1, b2, and omega, which is equal to the square root of the spring constant associated with the string over the mass of my object, and these are all constants. So these are just some numbers which we fixed by setting some boundary conditions or some initial conditions, right? We might say that x of 0 is equal to 1 and x prime of 0, or the derivative of x is equal to 0, whatever it may be. We choose those and fix these constants. And omega is a constant associated with the physical parameters of our system. Okay, so the interesting thing that we found was when we wrote down the velocity, vi of t, we just take a derivative of the position vector, or the components of our position vector, and we find something like minus omega ai sine omega t plus omega times bi cosine omega t. Okay, so then what we did is we took the cross product between these two vectors, so the x vector and the velocity vector. So we can do this two-dimensional cross product, x cross v, using this epsilon symbol, ij, xi, vj, where here we're using our summation convention, so I'll explicitly write the sum, so we're summing over both I and j. I'll write this even more explicitly, so I goes from 1 to 2, j also goes from 1 to 2, epsilon ij, xi, vj. And we just, since our indices are summed over, we just suppress these summation symbols, because otherwise it just all gets really messy really fast. And epsilon has this property where epsilon 1, 2 is equal to 1. And if I interchange any indices, so epsilon ij is equal to minus epsilon ji. So if I flip either two indices, I get a minus sign. Okay. So what happens when I actually do this, when I take this cross product? Come down here. So when I do this, I get something that looks like epsilon ij, xi, vj. So actually doing this sum, I get something like x1, v2 minus x2, v1. Because remember, if I have epsilon ii, well, I'll write this as epsilon 1, 1. This is going to be equal to minus epsilon 1, 1, which has to be equal to 0, and same for epsilon 2, 2. Right, because I can just exchange these two indices, but it gives me the exact same thing, and if anything is equal to minus itself, it has to be 0. Okay, so we have this expression. So now I just plug things in. I find that x1, v2 is a1, b2 times omega. And this is, there's nothing tricky going on here. We're just plugging in values for what we found before. A2, b1, sine squared omega t minus a1, a2, omega cos. It's not a very pretty expression, but it's the expression we get, plus b1, b2, omega cosine omega t sine omega t. And similar for x2 v1, we get something like a2 b1 omega cosine squared omega t minus a1 b2, oh, there should be an omega living in here, omega sine squared omega t minus the same thing. So a1, a2, omega cosine omega t sine omega t plus b1, b2 omega cos omega t sine omega t. Okay, so this looks pretty ugly right now. But when I actually take this difference, we can see that this term and that term are going to cancel. This term and this term are going to cancel. And this term here and this term here are going to give me something like minus a2 b1 omega times sine squared omega t plus cosine squared omega t. And this term and this term are going to give me something similar, but switching these two. Switching these two indices, so a1 and b2. But we know that this here, just from trig identities, is equal to 1. And so this just gives minus a2 b1 omega. So when all is said and done, when we actually take this cross product, or cross product being in quotes, we have epsilon ij, xi vj. And this actually ends up, pretty amazingly, being constant, minus a2 b1. This is a constant. So this should be pretty mind-blowing, because we assumed pretty much nothing about the system. We just took this system. We have pretty arbitrary numbers, or not just constants, where we could plug in pretty much anything. And at the end of the day, both the position vector and the velocity vector were functions of time. But when we take this cross product, we find that it's constant. Meaning, if I take the time derivative, d by dt, of this x cross v, I get 0. So this doesn't change with time. So that this, since we were able to get a constant out of something which is pretty general, right? It feels like something deeper might be going on. So let's try to explore this a bit more, and see if actually something is deeper is happening. And so what I want to do is I want to do a general cross product. So I'm gonna write just x cross v. And this could be in any number of dimensions, 1, 2, 3, whatever. Well, not 1, it just gives 0. But, so if I want to write the components of this, I can write this as I3, I4, up to ID. And this is epsilon I1, I2, I3, I4, all the way up to ID. X I1, V I2. Right, so this is just what I mean when I write down this cross product when we're talking about a general number of dimensions. This epsilon tensor behaves exactly the same way, where if I swap any two of the indices, I get a minus sign. But in general, it can have as many indices as the number of dimensions that I have. So I'm just going to call it x cross v for the time being. So I want to look at what happens when I take the time derivative of this guy, x cross v. Now, this is just a product of two things. Keep in mind, I'll write it explicitly. Both x and v can be functions of time. But so this is just a product. So I can use my usual product rule for derivatives on it. If you want to see it more explicitly, you can come up to this, I'll use this fancy thing. You can come up to this expression up here, and you can see that epsilon is a constant, and then x and v, the components of both of those, are going to be just some function of time. So I can use my product rule, and I get dx dt, so the derivative of the first, cross the second, plus the first cross the derivative of the second. But I know what these derivatives are. This gives me the velocity. This gives me the acceleration. And so when I take this time derivative, I get something like the velocity crossed with the velocity, plus the position crossed with the acceleration. But remember that the cross product picks out perpendicular pieces of vectors. But this case here, I'm trying to find the perpendicular pieces of two of the same vectors. Well, the same vector is always going to be parallel to itself, so it's never going to have any perpendicular component, and this first part automatically goes to 0. So what I'm going to do next is I'm just going to multiply this whole thing by mass, because that gives it a little bit more concrete of an interpretation. So if I multiply this guy by mass, and assuming we're talking about the entire mass of the system so that it doesn't change with time, I can pull it in and multiply it by the velocity to give a momentum. And here I can also pull it through and multiply by the acceleration to give a force, just by Newton's second law. And so what I find is d by dt of my position vector crossed with my momentum is equal to my position vector crossed with any force that I'm applying on the system. And I'm going to put this guy in a box because it's very important. And I'm going to actually just give these things names. So I'm going to name, and this is just a convention. So L, I'm not going to put any vector symbols or anything on it, because of the fact that in an arbitrary number of dimensions, this could have, it could be a 0 component object, it could be 2, 3, 4, whatever. It doesn't have to be a 1 component object. And same with over here, I'm going to give the name tau. And this guy here we call angular momentum. And this guy we call the torque. So in particular, we care about two cases. The two-dimensional case and the three-dimensional case. That's really all we're ever going to be dealing with. So in 2 dimensions, 2D, this is just going to be some scalar. It's not going to be, the cross product is going to be a scalar. And so this just becomes dl dt equals tau. And in 3D, both of these are going to be vectors. Really, there's pseudo-scalars and pseudo-vectors, but that's a little bit of a very not important detail right now. Okay, so we want to find a conservation law from both of these guys. So we can see that L is conserved only if tau equals 0. We know that tau equals the position cross F, the force applied, which means that there's two cases where this actually vanishes. The first is if there's no applied forces, in which case F equals 0, and this all is very simple. But there is a second case where all of my forces are parallel to my position vector, in which case there's no perpendicular components, and by the definition of our cross product, this is 0. So we see that the conservation of angular momentum is in a sense less restrictive than the conservation of standard or linear momentum, what we called p. And if we remember, we had dp dt is equal to the force. So the only case where p is conserved is if the force is equal to 0. So we have this second option where we still can have forces acting on our system and still have a conservation law. So this is very cool, actually very powerful, because of the fact a lot of the forces that we encounter in nature actually behave exactly like this, as we'll see soon. Okay, so now I want to take a bit of care with the three-dimensional case, because of the fact that we have to be a little careful about the direction that these vectors point. So if I have some cross product, A cross B, in 3 dimensions, so I'm only going to have a single free index, because this is going to be a vector quantity. This is going to be something like epsilon ijk, A sub j, B sub k. Okay, so we know, and I'll just give this at the end of the day some label v. Just it's some vector. So what do we know? We know that epsilon, just by the properties of epsilon, picks out the perpendicular pieces of A and B. But since no two indices can ever repeat, the free index has to always also be perpendicular to all of these other directions. Meaning that vi is always perpendicular to A, but, or I suppose this should be a vector, so v is always going to be perpendicular to A, and v is always going to be perpendicular to B. So it's always going to be perpendicular to both of them. But the direction of v is specified by a convention. If I define something which is perpendicular to both A and B, it's defined up to a direction. So we have sort of a freedom of choice, and the convention that's always used is typically known as the right-hand rule. So right-hand rule. And this one's going to really put my drawing skills to the test, where if I have two vectors we'll say A, this one's A, we'll say this one is B, and I want to find the direction of V. I'm going to take my right hand, and of course this is going to be a little bit difficult to describe over stream, but so I'm going to take my right hand, I'm going to point my index finger along vector A, and then I'm going to point my middle finger along the vector B, where, you know, the rest of my hand is down there. And then my thumb is going to give me the direction of the third vector. So in this case, so we'll say this guy is A, along A, this guy is along B, and this guy is going to give me the direction of V. So that's kind of how we conventionally talk about cross products like this, specifically the direction that the cross product gives us. And actually, this is always fun to see in typically Phys 1 exams, walking around the room. You always see students holding their right hands in funny directions to figure out which way the vectors point, which is a good thing to do. So I just want to do a quick example of this, specifically with angular momentum. So I'm going to draw my axes here. So we'll say this is E2, this direction is E1, and this direction is E3. Okay, so say I have some, I don't know, some particle up here, and it's moving in the direction, we'll say, I'll make this blue this way, where I can, yeah. So we'll say it's kind of going off in the sort of minus E1 and plus E2 direction. So this is going to be my momentum vector. And then I can draw my position vector, which is just going to be here. And we can use our right hand rule. So pointer finger along the x vector, middle finger along the momentum vector, and we see that our angular momentum vector is going to be something like pointed in this direction. Hopefully that makes sense. Okay, so I'll take a quick pause here and see if anyone has any questions before moving on to some, I think, some pretty fun stuff. We're going to be doing some cosmology stuff next, but this is kind of the basics. So if anyone has any questions, feel free to let me know. Take a drink of water. If not, we can move on. Yes, actually, one reason I like talking about angular momentum is because it has some very interesting applications, specifically to cosmology, and where you can solve somewhat non-trivial problems with very simple results, or with very simple concepts like angular momentum. So I'm not seeing any questions showing up. Let's go ahead and move on. I want to talk about Kepler's laws. So, a bit of historical background. Kepler came before Newton, so he didn't have any laws of gravitation to go by or anything like that. But he was able to come up with 3 laws that govern the motion of the planets in the solar system, based solely off of data collected by Tycho Brahe, a even earlier astronomer. So what we're going to start out talking about are the first 2 laws, and then later on we'll get to the third. And we're actually going to be able to get a lot of information about how gravity acts just from these few laws and these concepts that we've learned from angular momentum. So let's write down the first 2 laws. The first law is that planets orbit the sun in ellipses, where the sun sits at one of the foci of the ellipse. The important thing about this one is that, so ellipses are 2-dimensional things, so we can treat it as a 2D problem. The more interesting law is it's a little more abstract. So before writing it down, I'm gonna just draw out the scenario. So we're gonna say that our sun, draw it green as a green star here. Oops. Our sun sits here, and we have some planet, I don't know, or not, some planet going here, and it's orbiting around the sun in this elliptical motion. So what Kepler's second law says is that, okay, say I draw a line, we'll make it purple. So I draw a line from the, I'll actually make this a straight line. I'm going to draw a line between the sun and the planet. Now, as the planet moves through its orbit, after some time, the planet will be at some different location here. And this line will have swept out some area. I'll color it red here. So the sun will have, or the planet, or this line, sorry, which connects the sun to the planet, will sweep out some area here. Now I could do the same thing where when the planet's at a different point in its orbit. So say now the planet's over here, and this line in the same amount of time might sweep out a very different shape. So maybe something more like this. I'll color this one blue. So I'll write this as A1 and A2. And what Kepler's second law simply states is that A1 is equal to A2. So in words, this just means that this line, if I allow it to sweep out some area in some time, no matter where the planet is at in the orbit, as long as I look at the same time interval, that area is always going to be the same. So another way to say this is that if I'm looking at so say this planet is going around and around and around, sweeping out some total area, the change in that area, which I'll call dA, in some time, is equal to a constant. Okay, so how much the total area that this guy sweeps out changes in a fixed amount of time is always going to be a constant. That's Kepler's second law. And from these two things alone, we can find a very interesting fact about gravity and how gravity acts on bodies. So let's kind of zoom in on this picture. So I have my star here, and I have my planet here, and I have my line which goes here, and let's consider a very small amount of time, almost zero amount of time, in which case this area is going to essentially just be a triangle. So I'll just mark it in white. This is essentially going to be a triangle, which I can draw down here, kind of exaggerate it a bit, where one of the sides is going to be the position vector, which in this case I'll just call r. Earlier I used x, but in this case I'll use r. And another side is going to be some, I'll call this ds. So the distance that the planet has traveled in our time dt. But this is just going to be equal to the velocity of our planet times the time interval that we allow to elapse, this small time interval. Okay, so I'll just redraw this over here. This is going to be r, and this is going to be v dt. So how do we find an area? Well, if I double this triangle like this, dA, I know that the area of a parallelogram like this is given by the cross product of the vectors that make up the two sides. So in this case, I can write that 2 times dA, right, because I have 2 times the area that I actually care about. This is equal to r cross ds, which is equal to r cross v dt. Now I can rearrange things, and I find that dA dt is equal to 1/2 r cross v, and just multiplying this by a factor of 1, which is going to be the mass of the planet over the mass of the planet. This is 1/2m r cross p. But this, of course, scroll down a little bit. R cross p is just our angular momentum L. So this tells us that dA dt is equal to L over 2m. So this area that is swept out, so this small area here that's swept out in this given amount of time, is given in terms of the angular momentum of our planet. But as we already said, dA dt is equal to a constant. Which automatically tells us, obviously 2 is a constant, m is also a constant. This tells us that our angular momentum is also constant. In other words, the torque acting on the system has to be 0, which tells us that gravity only acts along our position vector. So it only ever acts from the center of our, so from our star, directly along the position vector to the planet. So this is actually really a really important result, and perhaps even a bit unexpected, because planets can speed up in their orbit, they can slow down in their orbit, so it's not necessarily trivial that this is only, or that it's not exerting any torques. So, okay, so that's our first very important result from smashing together both conservation of angular momentum and Kepler's laws. So I'll pause here again and ask if there are any questions before I move on to another cosmology application. Okay, well, I'm not seeing anything. So, okay, let's move on to our second application of these ideas. And this one's going to be a little bit less math and a little more just kind of thinking about how things work. And this one comes from a question that I think a lot of people have had when they're looking at, say, pictures of the solar system and pictures of the Milky Way. And the question is, why do these objects, so this our solar system is a great example, Milky Way is an even better example, these objects which live in three-dimensional space and are allowed to move up and down in all sorts of directions, they stay in a plane, all moving the same direction. So what's up with that? It's a pretty common thing. We find spiral galaxies like the Milky Way all over the place. Our solar system acts this way. Everything seems to be fixed in a plane. So let's see if we can come up with a satisfactory answer for this question. So when I have an object like this forming, I'm going to have some bunch of stuff all piled together in an area, right? So it might be dust particles like this, I might have some gas, whatever it is, but I'm just going to have some amorphous blob of junk, which will eventually become my galaxy, or my solar system, whatever it may be. Now, obviously gravity is going to act on between the different pieces, and these things are going to collide and bump into each other, but nothing's going to be acting from the outside. So if I just isolate this system, I know that all of my torques are going to be 0 acting on this thing. In fact, all forces as well are going to be 0 from the outside. Internally, there's going to be a whole bunch of complicated stuff going on, but as long as I isolate it in its own little bubble, all of the net torques are going to be 0. But that means that the total angular momentum, L total, and in this case we're talking about 3 dimensions, so this gets a vector quantity, L total has to be a constant, where L total is going to be the sum over all of the individual angular momenta of all of my particles, right? So, this one might be pointed in that direction, that one there, whatever it may be. So all of these are going to have some angular momentum pointed in all of these different directions. But the important thing is that I have a single vector direction picked out. I have a single angular momentum direction that is conserved. It's not the individual. It's not the individual angular momentum that are conserved, right? Because these things can collide and interact, and so the individual angular momentum will change, but the total angular momentum won't. So what will end up happening is all of these particles are going to collide, and they're going to hit each other and interact, and a whole bunch of complicated stuff is going to happen, but I have some net angular momentum. Well, I'll draw it here, L total. And all of the angular momentum vectors pointing in all the other directions have to cancel out, which means that given enough time, all of the particles with opposite angular momenta, or angular momenta not perfectly aligned along this vector, will find each other, and they'll hit each other. And that extra angular momentum in all these other directions will cancel out until all of the individual angular momenta vector are all pointing along the total angular momentum vector, right? So at the end of the day, everything is going to essentially look where all of these new vectors that I drew are going to be all more or less aligned with L total. So the interesting thing about this is that when I have a vector like this, it actually picks out a plane in 3 dimensions, right? If I draw a plane, I have some vector which is perpendicular to this. And in fact, my L total vector is going to pick out the plane, since it comes from a cross product of the 2 vectors which are perpendicular to it. And since all of the individual pieces now have their angular momenta lined up with this total angular momentum, I get a everything rotating in the same direction in the same plane. Otherwise, it'll find something else and cancel it out. So that's how we get, objects like our Milky Way forming, where we have this more or less planar spiral galaxy where all the pieces are rotating in the same direction. So it's, again, it seems like a very complicated question, but it all ends up being a fairly simple answer. All right. So now I'm going to move on to a bit more, I'll say, applied case, or a bit more applicable case, where let's say we have some mass, and I know that it's moving in a circle. Let's see if I can draw a circle. That's pretty good. Where this is going to have some position vector associated with it. It's going to have some momentum vector associated with it, and we'll say the radius of this guy is r. Now, my question is, what force do I apply to make this happen? And for the time being, we'll just assume that it's a central force. It's a force that acts only along this x vector. We'll make that assumption so that L equals a constant. Our angular momentum is going to be some constant value. And in this case, we can treat this as a 2-dimensional problem, where I'll name my axes, or my unit vectors, E1 and E2 again. Okay, so in this case, I can just write down the position vector. The position vector isn't too hard to write. And this is just going to be r cosine times omega t plus delta E1 hat plus r sine omega t plus delta. Actually, I'm going to rename delta to something a bit more intuitive. I'll call this phi 0. Okay, so what are these things? Obviously, r is the radius of the circle, t is the time elapsed, and phi is the angle that this thing starts at. So if I look at time 0 and say this is my E1 direction, and my mass starts here, this would be phi naught, where this is all at t equals 0. Okay. So what's omega? How can we interpret omega? Well, the argument of these sines and cosines is going to give me the angle that this guy is at, right? So at some later t, it might look something like this, where this is phi of t, and my mass is sitting somewhere like here. Okay, so I can write down that phi of t is equal to omega t plus phi naught. And let's assume that phi is a constant, as we'll see it is in a second. Then the time derivative of phi is just equal to omega. So this acts very similar. So I'll write an analogous case where if I have some position with respect to time, and it's moving at some constant velocity, then the change in the position with respect to time is given by v. So this omega is acting very similar to a velocity, a linear velocity, but instead for an angle. So because of that, we call this angular velocity, and we give it this name of omega. So, okay, so this guy here, it's pretty simple to show that it's actually moving in a circle, and one way we can do that is to show, I'll just call x of t, the magnitude of the position vector, which is, of course, going to be given by the sum, or the square root of the sum of the squares of our components, which is r squared cosine squared omega t plus phi naught plus r squared sine squared omega t plus phi naught, which is just equal to r, which means that this thing is always staying at a fixed radius as it moves around the circle. Not surprising. So this is definitely describing motion around a circle. Okay, so we want to find a force, which means we're going to want an acceleration, so we have to start taking derivatives. We'll take a first derivative with respect to time, dx dt, to get the velocity. And just looking up here, we can see that it's pretty straightforward. And actually, just for simplicity, I'm going to set phi 0 equal to 0. It doesn't really change a whole lot. Basically, you can think of it as we're just turning our heads so that, we're starting out just aligning E1 and E2 in this direction so that phi naught is 0. So I'm not going to worry about phi naught, but this is going to give me something like minus r omega sine omega t E1 hat plus r omega cosine omega t e2 hat. So that's going to be my velocity. Okay. So how do the position vector and the velocity vector relate? Or how do they orient with respect to each other? That's a pretty easy thing to find just by considering a dot product between the two. So I can take a dot product between the position vector and the velocity vector, which I can write in component form as the sum of the components. And this gives me something like, I'm just going to factor out a total r squared omega times minus cosine omega t sine omega t plus sine omega t cosine omega t, which of course is 0. So this tells me that my position and my velocity are always perpendicular. Okay, so that's pretty nice. So this tells me that since my angular momentum, I'm assuming, is constant, because again I'm assuming that my force is only directed along my position vector. So I'm saying my angular momentum is constant, and this is going to be equal to r cross, or in this case I call my position vector x, cross p, which is just mx cross v. But when we found these cross products, we found that this is going to be equal to m times the magnitude of x times the magnitude of v times the sine of the angle between the two. But since they're always perpendicular, this angle, so I'm always going to have something like this, where this is my position vector and my momentum vector, or my velocity vector, is always at a right angle with respect to that, so that's pi over 2. And this guy is just 1. So L is equal to m times the magnitude of x, which is just r, times the magnitude of v. Well, it's not super hard to show that the magnitude of v, which I'll just call little v, so I'll write this down here, little v is equal to the magnitude of v, which is the square root of r squared omega squared sine squared omega t plus cosine squared omega t, which is just r omega. So this is equal to m r squared omega. And this is actually a very important expression that will be used later on for sure. L equals m r squared omega. And since L we know is constant, the mass is going to be constant, the radius we know is constant because it's traveling in a circle, that confirms to us that omega should actually also be a constant. Okay. Excellent. So now we have the velocity. So we got to do one more derivative, and that's going to give us the accelerate. Oh, actually, I want to do one more thing here. So I have this expression that v is equal to r times omega, which tells me that I can write my angular velocity in the case of circular motion in terms of my linear velocity, just by this expression here. And this is going to be another very important expression. Okay, so now let's go ahead and find the acceleration just by taking another derivative of the velocity. When we do that, we get something that looks like minus r omega squared cosine omega t e1 hat minus r omega squared sine omega t e2 hat. But this is just equal to minus omega squared x, our position vector. Right, because our position vector was r cosine omega t e1 plus r sine omega t e2. So it's really easy to find the magnitude of this guy, and we find that the magnitude of the acceleration is just equal to omega squared times the magnitude of the position, which is just r. So this is r omega squared, which I can rewrite using this formula here, and this gives me v squared over r. Now this comes up all the time. This expression shows up everywhere. And so now I can rewrite this guy. So I know the magnitude, I know the position, or the direction that the acceleration acts. So I can rewrite this as a of t is equal to r omega squared x hat, which is also equal to v squared over r x hat, where x hat is the unit vector which points in the direction of x. These should have minus signs as well. In other words, x is equal to the position vector over its magnitude, which in this case is just r. Right, it's just something with length 1, which points in the same direction as the position vector. So I know the force, which is just going to be the mass times the acceleration. I'll put a little subscript c on it. This is mass times the acceleration, which is minus r omega squared, m r omega squared x hat minus mv squared over r x hat. I'm going to do another big box around this guy. So again, we see that our initial assumption was correct, or our initial we're not contradicting ourselves by assuming from the beginning that we had some central force, because we have something only acting in the direction of the position vector, and now we found how strong this force has to be to keep this thing going in a circle. And that is just the magnitude, which is mr omega squared, m, which is mv squared over r. And this is known as a centripetal acceleration, or centripetal force. Centripetal meaning center seeking. Okay. Excellent. Okay, I'm going to take a quick pause, see if people have questions, and then we're going to move on to actually applying these centripetal forces to particular cases. First, we're going to talk a bit about this kind of a subtlety with angular momentum problems, where we have to be a little bit careful about how we choose to approach them. And then and then we're going to tackle Kepler's third law to actually get a almost expression for a law of gravity. It's not going to be quite complete, but we're going to get close. So I thought it was centrifugal. Is there a difference? Yes, actually, there's a big difference between centripetal and centrifugal forces. Centripetal forces being forces that act inward to keep things going in a circle. Centrifugal forces being essentially the equal and opposite force that shows up from Newton's third law. So in a lot of cases, so say you're in a box here, and that box is spinning around. What you're going to feel in this box is some force pushing out, but you're also going to feel some force from the wall pushing you in. This is the centripetal force, and this is the centrifugal force. I don't want to write F sub c for both. But so, yeah, so they're an equal opposite force, as there needs to be from Newton's third law. The centripetal force acts inwards, centrifugal force acts outwards. Okay, cool. So let's go ahead and talk about something which I don't know about you, but it might raise some red flags if you're seeing this. So I'm going to write down my 3D angular momentum, which is x cross p, where x is my position vector, p is my momentum vector. Now, in the case of just regular momentum, this is my dv dt times the mass. Whoops, oh, sorry, this should be mass times the velocity, which is dx dt. Meaning that for the momentum, if I shift my origin, so if I make some shift in x, x goes to, I don't know, some x plus r, where r is some constant vector that I'm shifting the origin by. As long as r is a constant, it doesn't change the momentum. But it does change the angular momentum. So it seems like if I have one coordinate frame where I choose the origin in one place, angular momentum might be conserved, whereas if I choose it in a separate place, it might not be conserved. And in fact, this is true. So how can we reconcile all of this? So let's go ahead and show that. So we'll just start out, or we'll just do this with a, well, we have some particle. We'll consider 3 dimensions. So I'll draw my coordinates like this. E1, E2, E3. This isn't necessarily my origin, this is just defining where my axes lie. And we'll say that this particle is traveling in some circle which might look like this. Has some momentum vector associated with it. But now the question is, where do I put my origin? And, you know, a smart place would probably be directly in the center. It all seems very symmetrical in the center of the circle. In that case, my position vector, which is going to be here, it always has the same magnitude, and it'll be like exactly the case that we saw before. Okay, so here we already found the consequences of this, right? What we just did showed that we have some centripetal force, which is equal to minus mr omega squared x hat. We have some angular momentum, which is equal to mr omega. In this case, we have to use the right-hand rule. And so we can see that just by quickly using the right-hand rule that our angular momentum vector in this coordinate is going to be in this direction. And I don't know, I'll just call this L hat, whatever direction this may be. This might not necessarily just be in the E3 direction. I'll just call it some unit vector in the correct direction. But okay, so we know that angular momentum is conserved, which means that I have no torques acting on this system, right? And we can obviously see that because x cross fc is mr omega squared x cross x hat, which is obviously 0, because x and x hat are always going to be parallel. Okay, so now let's say I shift my origin to someplace new. So I'm just going to take all of this discussion and move it down. I stole the E1. I'm just going to delete that guy and rewrite him here. So now I'm going to shift my origin, and I'll do some new origin over here. So that the relation between the new origin and the old origin is going to be some vector r. It's going to be some constant vector, some number, or not some number, but this isn't going to change with time. My new origin isn't going to be changing places. This means that I can draw some new position vector here, which I'll call x prime. And hopefully it doesn't take too much convincing to show that x prime is equal to, right, I'm adding tip to tail, r and x. So this is just the vector sum of r and x. So that's by the position of this mass from this new origin. So now we can ask what my angular momentum looks like. Well, first I need to figure out what's happening with the direction of the momentum, but dx dt, or dx prime dt, is going to be dr dt plus dx dt. I know that r is a constant vector, so this is just the same velocity, which means my momentum vector doesn't change. Which we already said. We already said that under shifts of origin, momentum doesn't change. So that's good. Now how about angular momentum? Well, I know that L, I'll call this L prime now, is going to be x prime cross p, right? Because the momentum we just found doesn't change. But I can split x prime up, and this is r cross p plus x cross p, which this is equal to the angular momentum in our old coordinate system. So I get some r cross p plus, I'll just call it L, unprimed. Okay, so now I can ask, is this conserved? And I can find that by just taking a time derivative of this. And what I find is that I get something like r cross f and the only force acting on this is the centripetal force. So this is Fc plus dl dt, but I know that that's 0. But the centripetal force doesn't necessarily act in the same direction as this constant vector r. So it looks like in this new coordinate frame, L prime is not conserved. And it doesn't just look that way, that's how it is. So how do we reconcile all of this? Well, the hint might be in how this guy looks. So let's look at the torques on the system. Torque prime. Well, again, this is just x prime cross fc, which is equal to r cross fc plus x cross fc. We know that this is 0 because the torques vanished in our old coordinate system. And this is equal to exactly dl dt, as it should be. So what we've done is we've shifted our origin, and by doing that, we've made it so that the force no longer acts parallel to our position vector, which means, of course, we have a new torque showing up, which means, again, of course, our angular momentum should not be conserved. So when we're doing this, when we're doing these angular momentum problems, it's always important to try to be smart about where we choose our origin to be. Now, in the same vein, I want to talk about how symmetry can actually help us a lot. So now, instead of having two particles, or instead of having one particle, let's consider having two particles going in the same circle, radius r, but always on opposite ends of the circle. So in our original origin, or from our original origin, this guy is going to be measured some distance vector x, and this guy is going to be some distance vector minus x, because they're always on opposite ends of the circle from each other. And we'll say that this one has momentum p, and this one has momentum minus p. Hopefully this makes sense because the velocity is just going to be the change in x, and since this x is minus this x, then of course the velocities are just minus each other. Okay, so in this system, what is the angular momentum? L is going to be equal to, well, we have the first particle cross its momentum plus minus x cross minus p, which is going to give us the angular momentum of the second particle. But the minuses cancel out, and so I just have something like 2mr omega times L hat. Okay, so what happens now if I do the same thing I did before? I shift my origin by some amount so that this is now some vector r away. I have two new position vectors. Call this one x1 and x2, because these no longer have to be opposites of each other. They can be sort of general vectors. But I know that x1 is equal to r plus x, and x2 is equal to r minus x. Just from vector addition, add these things tip to tail, and I get these position vectors. So now let's do this same thing as before. Let's try to find our angular momentum in this primed system. And what I get is I want x1 cross p plus x2 cross minus p, because remember, the momentum doesn't actually change when I go to this new origin. Now I can just expand all of this out, and I get something like r cross p plus x. I'll just call this L over 2. And actually this will be minus r cross p plus, again, L over 2. And here we see that these two contributions actually exactly cancel out. And so now, whenever I shift my origin, because of the symmetry of the system, I always have the same angular momentum vector. Now, this will be really helpful if we consider, say I have some solid disk, which is uniform, and it's rotating. Well, I'm always going to have two pieces of this opposite the center. So I know that the angular momentum, no matter where I choose my origin to be, will always be the same. So when we consider cases like this, these extended objects, as they're typically called, this idea is really helpful because it takes this sort of arbitrariness of where we choose our origin out of the question. Okay, I'll pause again, see if anyone has any questions here, and then we'll move on to Kepler's third law and going towards a force of gravity. Okay, well, I'm not seeing anything. So let's go ahead and tackle Kepler's third law and then wrap things up. So Kepler's third law says this. I'll write it in words before explaining it. So the square of a planet's orbital period is proportional to the cube of the semi-major axis of the orbit. Okay, so in English, what does this mean? This means I have some star, draw it here, and I have some elliptical orbit, which looks something like this. Okay, so the orbital period is just saying, okay, it takes some time for the planet to go around this orbit. So the time it takes, so I'll call this delta t. I'll define this as a capital T. That's the orbital period. So it's the time that the planet takes to go one full orbit around the star. The semi-major axis is, I can divide this ellipse into sort of two pieces. The short piece, so the shortest distance between sides, and the long piece here. So the longest distance between two sides. And the semi-major axis is this distance here. So the piece from the center, the very center of the ellipse, to the farthest side of the ellipse. And that I'll call A. So what Kepler's law is telling us is just that t squared is proportional to a cubed. So the square of the orbital period is proportional to the cube of the semi-major axis. So let's simplify this a little bit. Let's consider only a circular orbit. So a circular orbit. We'll say it has radius r. Radius r. And some angular velocity omega. So we already found that gravity acts only radially, so it only acts along the position vector, which means that the angular momentum is conserved, and also that omega is a constant. We also found this expression that the angular momentum is going to be equal to, the magnitude of the angular momentum is equal to r squared omega. Okay, so it has a constant angular velocity as it goes around the circle, which means that some, if I have some delta phi, so it changes some angle. So I have the planet here, and it goes around its orbit, some angle delta phi. Well, that's just going to be equal to omega times delta t. But if I want to relate this to the orbital period, I have to figure out when this goes around the full circle, in which case delta phi is equal to 2 pi, which then tells me that, and this should be equal to omega times the change in time, which we've defined as the orbital period, which means that omega I can relate to the orbital period as just 2 pi over t. Now we have a circle, which means that there's no difference between the semi-major axis and the semi-minor axis. They're both just equal to the radius of the circle. Which means that A, our semi-major axis, is just equal to the radius of the circle. So Kepler's third law tells us that t squared is equal to, I'm just going to call this some 1 over beta r cubed, where beta is a constant. This is just saying exactly what we said before, that the square of the orbital period is proportional to the semi-major axis cubed. Where in this case, I just chose 1 over beta as our proportionality constant. Okay, so we know that the force of gravity has to be acting inward. It's keeping this in the circle, which means it has to be a centripetal force. So this is mr omega squared x hat, where x is just our position vector, as always. So the magnitude of this force is going to be given by just mr omega squared. But now I want to plug in this expression for omega. This tells me that Fg is equal to 4 pi squared mr over t squared. But now we have this t squared in the denominator, which means we can replace it with the corresponding expression with r cubed. So we know that this is 4 pi squared m beta times r over r cubed. Well, 1 power of r cancels, and I have something which looks like, I'm just going to call it alpha over r squared, where alpha I just defined as this whole mess of constants. Okay, so I'm going to write that a little bit more clearly as the force of gravity is equal to minus alpha over r squared x hat. So we found, based only on Kepler's third law, well, Kepler's 3 laws, we found almost a force of gravity, up to some proportionality constant. So we know that gravity acts only in the direction of the position vector, and from this we found that gravity is related to the square of the distance between 2 objects. So the only thing left to do is to find alpha, which consider later on. But so this is kind of one of these amazing things about being able to use these sorts of conservation laws, and how powerful in particular angular momentum can be. But so on that, I think I'm gonna ask if there are any more questions, and if not, I think I'll leave it there. Well, all right, I'm not really seeing anything. So with that, I'll say, if you're watching this now, thank you for watching. If you're watching it later, again, thank you for watching. Hopefully I'll see you on the next one.